practice writing the standard equation for an ellipse. First of all, what is an ellipse? More commonly, you might refer to it as an oval. It's the set of all points in a plane whose distances to two fixed points add to the same constant. So if you take a look at these diagrams, you'll notice a couple of key things here. So first of all, because these don't have perfect symmetry like a circle, we have to introduce additional vocabulary to help us describe the ellipse. So notice that there's no radius, because radius would mean that there was equidistance between the center and each point on this shape, and that's not true. We do have vertices at the endpoints instead. You describe the vertices as the endpoints of the major axis. Co-vertices are endpoints on the minor axis. So because this shape is a horizontal ellipse and therefore is longer on the x-axis, our x-axis is our major axis. On the other hand, if you look at the vertical ellipse, we know it's a vertical ellipse because it's the y-axis that dominates this figure. So vertices are the endpoints of the major axis, co-vertices endpoints of the minor axes, and then we've got focus, which are two fixed endpoints that they refer to. So when they say distances to two fixed endpoints add to the same constant, that means I could look at any point. So let's say I take this point right here. If I measured how far it was from here to here and here to here, I added those two distances together, I would get a certain answer. If I did this again and I measured from this point to the foci to here, I'd get the same sum. Continuing, if I did, I don't know, let's pick a crazy point, so point here, and I measured from there to there, I'd get the same thing if I added the distances together. If I did this point here, and I did here to here. So if I added up the two lengths of each of these, I'd get the same result. I'd get the same distance, the same constant each time. So no matter where I drag and where I measure the point to each of the foci and add together, I'd get the same result. Now, let's practice with the distance formula. Okay, so we know, hopefully you watched my video on circles, so you know a bit about the distance formula, and you know that if we want to know the distance between 2 points that aren't perfectly left, right, up, or down of one another, I measure the distance between these two by saying, okay, what's the distance or the difference in the y direction? What's the change? That triangle means change, or delta y. How much did I change, go up or down, in the y direction? How much did I change, go left or right, in the x direction? Using that information, I'm able to figure out this distance using the Pythagorean theorem. Because in this case, if you think of our sides as a, b, and c, the change in y is basically a, the change in x is basically b, and we're figuring out c. Just as here, in the distance formula, you can see that they are measuring the distance between one x and another, and they're measuring the distance between one y and another. So same mechanism going on. Now, we use an altered version of the distance formula for finding constant sum of ellipse. It looks like this. Notice what's happening. If you remember, if I had this focus, or this ellipse that maybe looks like this, let's say I have a foci here and here. If I wanted to know the constant sum of the ellipse, let's say I take this point into consideration and I say, I'm going to measure the distance from here to here. That's going to be one distance. And then I'm going to measure the distance from here to here, the second distance. So I've taken a random point on this ellipse and I'm measuring the distance from that point to the first focus and the second focus. Then I'm going to add these two distances together, and that is called a constant sum, and that's the number that we refer to when we say no matter what point, if we measured the distance between the point and the two foci and added that distance together, we'd get the same number. That's exactly what we're doing here. We're saying, well, what is that same number? This is how we're solving for it. So this is just a slightly more sophisticated version of the distance formula. What's happening is that we're making two measurements. So not only do I have to find the distance in the x direction from here to here and the y distance from here to here for the first foci, I have to do it again for the second foci. So I'm finding the distance from my point to foci number 1 and then my point to foci number 2, which is why you see these two different sets of computations being done here. Now, the most important thing to remember when filling in this equation is that I am measuring the distance, again, I'm measuring the distance from a point on the ellipse and comparing it to one foci and then the other. Meaning, I need to strategically decide which coordinate set, so I've got a coordinate for the foci 1, I've got coordinates for foci 2, and I've got coordinates for a point on the ellipse. My point on the ellipse must be assigned to x3, y3. The point on the ellipse must be assigned to x3, y3, and this is always the case. Here's why. Notice that x3, y3 appears twice. It's because the first time x3, y3 is being compared to one focus, and the second time that point is being compared to the other focus. If you find yourself in a situation where you have all of the coordinates of the two foci under one radical symbol, you know you've done something wrong, because that means you are now measuring this distance, the distance from focus to focus, and we don't care about that, so let's not measure it. So let's set this up. I'm going to write out the skeleton, as you might know I like to do if you've watched my other videos. I'm going to set up the skeleton of this equation. And here's what it looks like. So I put in all my radical symbols, I put in all my parentheses, I put in all my subtraction signs. And then it's as easy as going back and matching my coordinates to the descriptions in the question. So again, as I said, the point on the ellipse must correspond to x3, y3. So x3 is 9. So I'm going to go through and I say, great, x3 is 9, put a 9 there. x3 is 9, put a 9 there. y3 is 8, perfect. 8 goes here, 8 goes here. It doesn't matter if you assign, how you assign the remaining. So foci 1 could be assigned to x1, y1 or x2, y2. It's interchangeable, it doesn't matter. I normally just assign them in the order that they appear. So since they mention this coordinate first, generally I'll assign that to x1, y1, but again, it doesn't matter. So let's go ahead and do that. All right, so I'm going to call x1, y1 3, 0. So if x1 is 3, I'll write a 3 here. y1 is 0, I'll write a 0 here. So notice that this coordinate only appears once in the equation. Foci appear once each in this equation. x2, y2 is 24, 0. So now I've got my setup done. Let's continue. From here, it's just a matter of simplification. So 3 minus 9 equals negative 6. 0 minus 8 is negative 8. 24 minus 9 is 15. And 0 minus 8 is negative 8. Double check our work. Oh, forgot that square. I knew something was missing there. Okay, so I've got negative 6 squared plus negative 8 squared, 15 squared, negative 8 squared. Just continue simplifying from here. 6 squared is 36. 8 squared is 64. 15 squared is 225. 8 squared is 64. Continuing further, this gives me the square root of 36 and 64 plus the square root of 225 and 64, which would be, what, 289. The square root of 100, keep going, Square root of 100 we know is 10. Square root of 289 is 17. So our final answer becomes 27. So the constant sum for this ellipse is 27, meaning if I take any point on this ellipse and I measure the distance from my point to my first focus, my point to my second focus, and I add those two distances together, I'll get 27. Let's practice again. All right, so constant sum, this should be a plus sign. Here is our formula. Let's get to work. We're given focus 1, focus 2, point on the ellipse. Now, remember the point on the ellipse must be assigned to x3, y3. So x3, y3 must be 9, 0. Let's start with that. So I'm going to write out my framework. Now you could, if you wanted to, try to fill this in left to right. So you could start by finding x1, then finding x3, then finding y1, finding y3. I find that that tends to be a little bit more confusing, and it's better to just take a few passes at the equation and fill it in bit by bit rather than filling it in left and right. So I know that x3 is 9, so I'll find x3, write 9. y3 is 0, so 0, 0. Next up, let's call this guy x1, y1. Again, it doesn't matter, so x1, y1 is 3, 0. So 3, 0. And that leaves us with x2, y2. So x2 is 24, y2 is 0. From here, we continue simplifying. So we get 3 minus 9, which is negative 6 squared. A note of caution here, remember to carry this square root with you throughout the whole problem. It's easy to accidentally drop it. That is a frequent mistake, so just watch out for it as you go. 24 minus 9 is 15. 0 minus 0 is just 0 squared. So these zeros don't really matter, right? I didn't have to write them down. So what's the square root of 6 squared? 6, right? I don't even have to know what 6 squared is. The square root of 6 squared is 6. And the square root of 15 squared is just 15, right? So my distance is equal to 21. So that means my claim is that if I have this ellipse and I take a measurement, a random point, so if I go right here and I measure the distance from here to here and here to here, we'll call that D1, distance 1 and distance 2. I'm saying that distance 1 plus distance 2 equals 21. That's the constant sum for this ellipse. Let's do one more example. This will be our last one. All right. So we've got our equation in front of us. And let's start this time just with the framework. Get that out of the way. It's a little tedious to rewrite this over and over. It does get a little tired. However, I do find that it, again, minimizes my mistakes. It's a little more organized and easy to approach this way. Okay, so what do we know? We know that the point on the ellipse must be x3, y3. So x3 is negative 21. Don't forget that negative symbol. x3 is negative 21, and y3 is 0. Keep going. I'm going to call this guy x1, y1. x1 is negative 20. You know what? I don't know if I like that. No, I'll leave it. So x1 and y1 would be 0. So what was just going on was I was thinking, I don't know if I want to have to deal with larger numbers that I'm going to get if I put my 20 and my 21 together. So I was thinking about rearranging and calling this guy x1, y1 instead, but I decided not to. So this guy is now x2, y2, so I've got x2 here, y2 here, and continue on. Negative 20 minus negative 21. Negative 20 minus negative 21. So this becomes addition. These cross each other out. So what's negative 20 plus 21? It's positive 1. So I get 1 squared plus 0 minus 0 is 0. So that was easy. On this side, I get 20 minus a negative 21, so this becomes addition. So 20 plus 21 is 41. 0 minus 0 is 0. So now I've got, and as you can see, I've dropped these square symbols a few times. Be really careful with those as well, because the nice part here is that the square root of 1 squared, these undo each other, it's just 1. The square root of 41 squared, I don't know what 41 squared is, but I do know that this square root and this square symbol cancel each other out. So my distance is equal to 42. So this is the constant sum, and again, one last time, if this is my ellipse, and I've got my first focus and my second focus, and I put a point on the ellipse, I measure this distance, I measure that distance, I add them together, I will get 42. No matter where I put my next point, my addition, my D1 and my D2 will be different, but they will always add to 42.